So we've looked at calculating the limits of series up to a certain number of terms. What we're going to do is we're going to stretch this out in this video, and we're not going to stop at an upper term. What we're going to do is figure out how we can calculate the limit of an infinite series, both geometric and arithmetic, and if they exist or not. We have to be able to do this with some of the work that we are doing. So what we're going to have to do is figure out what conditions we need to satisfy for this limit to exist, if it does, and then how we can use this to calculate the ultimate value of the series. First, let's focus on an arithmetic series. Now remember, we said before that the sum to n terms of any arithmetic series is given by this relationship here. So a half n bracket 2a plus n minus 1 times d. Now remember, each part of this comes from parts of our generalized term of it, which is given by un equals a plus n minus 1 d. So a is our starting term, d is our difference, so what it goes up in each time, and n is the number of terms that are there. Now to figure out how this goes, first thing I'm going to actually do is take this and expand it. So what I'm going to do is take this whole bracket here and rewrite that as 2a plus nd take away d. What I'm going to do is I'm then going to group together the terms without an n value to it. So what I'll do is I'll rewrite that then as 2a take away d, and I'm going to put that in a bracket to show I'm grouping them together, and then I'm going to have a plus nd after that. Now remember, I've not got rid of this part here, I'm just expanding inside the bracket there. So what I've then got is a half n multiplying that entire bracket out. Now, let's imagine what I'm going to do is take inside this bracket and do a little bit more to it. Let's imagine I want to get rid of the n associated with this d here. So I'm going to take it outside the bracket as a common factor. So I've got a half n squared outside my bracket. Well, for this part here, this would just leave me with a plus d. But I'd have to divide this term here by n to counteract the fact I'd have an n squared going into the bracket, so I'd have the extra n coming from that. So that first term would then be 2a minus d all over n. So that's the sum to n terms is equal to that. Now let's imagine we're going to look at as n, the number of terms, tends towards infinity. Well, as n tends towards infinity, what's going to happen is if I put that into this fraction here, 2a minus d over n is going to become a fraction where the denominator is going to get continually bigger and bigger and bigger and dominate that whole fraction. As n gets bigger then, that fraction gets smaller and smaller and smaller. So as n tends towards infinity, this fraction here tends towards 0. So what I can say at that point then is that n tends towards infinity. What that means is the sum to infinity tends towards getting rid of this n squared d over 2. Now here's the problem with this though. As n gets bigger and tends towards infinity, the top of this fraction tends towards infinity as well. So it's just going to continually get bigger and bigger and bigger. So the issue with that then is I've got no sum to infinity. Yeah, it's undefined for an arithmetic series. So that's one thing we have to remember. As it gets bigger and bigger and bigger, we don't get a set value for it. We have no formula that we can do. So as n tends towards infinity, for an arithmetic series, the sum to infinity tends towards plus or minus infinity depending on the value we're going towards here. So we have no formula for the sum to an infinite number of terms of an arithmetic series. Let's imagine we look at a geometric series then. So for a geometric series, we know the sum to n terms is equal to a bracket 1 minus r to the n all over 1 minus r. And we know that a generalized term for a geometric series is given by un equals a r to the n minus 1. And for this, our a is our starting term, u1, and the r we know is the common ratio. So the ratio between two consecutive terms. Now, what we have to ask ourselves is, right, what happens then as n tends towards infinity for this one? So what's going to happen? Well, there's actually two cases, and the key part to focus on is the r. The key part to focus on in this one is the r, because there's two cases of what can happen here. And we've seen it in some of the examples. We've seen examples where the magnitude of r is bigger than 1. So we get a common ratio where it's getting bigger and bigger each time. We've also seen where the magnitude of r, our common ratio, is less than 1. So it's a fractional amount between -1 and 1. Each of these has a different net result. So let's imagine I'm going to look at where the magnitude of r is greater than 1 and where n tends towards infinity. Well, what's going to happen is this term here, the r to the n, is going to dominate the entire fraction here. It's going to dominate everything that we've got. So as this power gets bigger, because this number is larger than 1, that's going to continue to get bigger and bigger and bigger each time. So as n tends towards infinity, r to the n will also tend towards infinity. So that will just get bigger and bigger and bigger. So if I've got an r, a common ratio, which has a magnitude bigger than 1, what's going to happen then is that the sum to infinity is also going to tend towards infinity. So again, it's the same principle as the arithmetic series. It just gets bigger and bigger and bigger. There's no way the terms can get smaller. It's going to tend towards infinity itself. Now let's imagine I'm going to take the magnitude of r to be less than 1 as I look at n tending towards infinity. Again, let's focus on this r to the n term. Now, r to the n, something to a power of n, where it's a decimal, as that power gets bigger and bigger and bigger, what's going to happen is the value is actually going to get smaller and smaller. So let's imagine we take a half. If we've got a half and we do a half squared, that's a quarter, so it's getting smaller. If we then do a half cubed, it's 1/8, so it's getting smaller. If we then do a half to the power of 4, we get 1/16. So as we raise that power, what's happening is the overall fraction is getting smaller. So what we can say is that as n tends towards infinity and this continually gets bigger, r to the n in this case is actually going to tend towards 0. Eventually it will get to a point where it has no contribution towards what we're doing with it. So it's going to tend towards 0. So what that then means is that my sum, as I tend towards infinity, this r to the n term is going to vanish. And the only thing that's going to happen is what I've got left. So my sum to infinity is going to be a over 1 minus r. So if I have got the magnitude of r being less than 1, my sum towards infinity for a geometric series is going to be that. That's the condition it has to satisfy. This key bit here is that magnitude of r has to be less than 1. Now it doesn't matter if it's a negative number, so I could have negative a half or a half. The same thing will happen. It's the size of the number that is the key issue here. A common ratio has to be less than 1 for it to get smaller and smaller, regardless of if it's a positive or a negative number, and that's the condition we have to satisfy. So to summarize all of that in one slide, what we can say is that for an arithmetic series, we know that the sum to n terms equals a half n bracket 2a plus n minus 1d, and as that n tends towards infinity, so our sum s to infinity, what we could say for any arithmetic series is undefined. For a geometric series, we know that the sum to n terms is given by a bracket 1 minus r to the n, all over 1 minus r, and the sum to an infinite number of terms, so s infinity equals a over 1 minus r, but only when the magnitude of r is less than 1. So only when our condition of the magnitude of r is less than 1. So let's imagine we'll look at this in a couple of questions. Let's imagine I ask you the question, does the sum to infinity of the geometric series 36 plus 12 plus 4 continue exist, and if so, what is it? Well, the first thing you need to answer is, does it exist? And in order for that, what we have to figure out is the magnitude of r less than 1. And remember, r, our common difference, is the ratio of consecutive terms. So in this case, I do 12 divided by 36, or I'd do 4 divided by 12, looking at what these are. So 12 divided by 36 is a third. 4 divided by 12 is also a third. So what that means then is that the magnitude of r is less than 1. So we can say, good, it exists. Now we have to say to ourselves, what is it? Well, we know that S infinity for a geometric series is given by a over 1 minus r. What we need to figure out is what a is and what r is. Well, we know that a is our first term u1, which in this case is 36, and r, we've just calculated it, is a third. So substitute it in and we get what we're after. So we know our S to infinity is a, 36, over 1 minus a third. So 1 minus a third is 2/3, so it's 36 divided by 2/3, which in this case, remember, turn it to a times, flip the second fraction, so it's 36 times 3 over 2, so 36 divided by 2 is 18, 3 18s are 54. So there you go. My sum to infinity for this geometric series is 54. Let's imagine I ask you this question then. Express the recurring decimal 0.1515151, continuing on like that, as a vulgar fraction. What we can do with this one is, first thing you need to do is look at the number and figure out to yourself, is there some sort of pattern? Well, imagine I split it every 2 terms. If you look at that, it's 1 5 and then a 1 5 and then a 1 5. So what I'm able to then do is say, fine, so 0.151515 continuing on, that can be written as 0.15 plus 0.0015, then plus 0.000015, and continuing on. So I'm going to add that on every single time as it goes. Now let's imagine then I'm looking at this in terms of a geometric series. What I'd be able to say is, if this was a geometric series, so I know my generalized term is un equals a r to the n minus 1, I'd be able to say that a would be equal to 0.15. What I'd do for my r is I'd look at the ratio of consecutive terms. So for my r, I could do 0.0015 over 0.15. Figure out what that is. So the ratio of this consecutive pair of terms here would be 0.01. If I looked at any other 2 terms as well, I'd find the same thing out. So if I looked at the ratio of these 2 terms here and did 0.000015 over 0.0015, I'd also get 0.01. So I can look at that and say, right, so I'm just adding that on every single time. A key thing to look for when it comes to being able to say I can express it as a geometric series is, quite simply, there's a repeating section here, as I pointed out at the first part, but this second 15 can be represented by something multiplying the first 0.15. So if I take 0.15 and multiply it by 0.01, what I'm going to get is 0.0015. If I then square the 0.01 and multiply it by that, I'd get the exact same thing, but in this case I'd get an extra 2 zeros, so I'd get 0.000015. So it's a recurring pattern in terms of that, so I'm able to think of it as a geometric series. Now this is going to continue on and on in terms of 15s, 15s, 15s the whole way, so what I can do is say to myself, what then is going to be the sum to infinity? Well, the sum to infinity is going to be this, but continuing on and on forever. Now I know, just by looking at this, that my magnitude of my r is going to be less than 1. 0.01 is less than 1, so my limit exists. So for that, I would just substitute in what I know. So my a is 0.15 over 1, take away my r, 0.01. And if you plug all that together, what you end up finding is you get 5 over 33. So the sum to infinity of that would be 5 over 33. If you fire that in a calculator, that number there is what you'd get. Just a couple of examples of how we can use this and the kind of applications we need to think of.